questions 21 through 25 on the 2013 Grade 10 AMC 10A. A group of 12 pirates agree to divide a treasure chest of gold coins among themselves as follows. The kth pirate to take a share takes K over 12 of the coins that remain in the chest. The number of coins initially in the chest is the smallest number for which this arrangement will allow each pirate to receive a positive whole number of coins. How many coins does the 12th pirate receive? Well, let's make a little bit of a table, but hopefully we don't have to go too far to see a pattern. The first pirate comes along and he's going to take 1 over 12 since K is 1. He's the first pirate. So let's say N is the total number of coins. So he comes along, he's going to take 1 over 12 of the coins. So he's going to take N times 1 over 12. After he does, how many coins are left? Well, how many coins are left are N minus N over 12. So 11 N over 12 coins are remaining after the first pirate takes his share. Now let's go to the second pirate. Now K is equal to 2. Remember, we have this much remaining. So the second pirate will take, since K is 2, 2 over 12 of the amount that's remaining, which was 11N over 12. Now this is how much he takes. So how much does he not take? Well, he takes 2 over 12, so he doesn't take 10 over 12, right? And we have to multiply that by how much was remaining. So this is the amount he takes, and this is the amount he doesn't take. So therefore, if he doesn't take it, that's the amount that's remaining. Okay? And similarly, when K is equal to 3, we have K over 12, which is 3 over 12, representing how much that third pirate takes. Now, what does he take? What is remaining, which is that. So 11N over 12 times 10 over 12. That is what he takes. What he does not take is what is remaining. If he takes 3 over 12, he does not take 9 over 12. So that's what's remaining. So this is 10 over 12 times 11 over 12. So hopefully you might be seeing a pattern here. I'll do a few more just in case you're not. Let's do 2 more. K equals 3 and then K equals 5, and then hopefully by then you'll see that pattern. When K is equal to 4, that is the fourth pirate, so 4 over 12 is what he takes, but what he's taking is this, 4 over 12 of that. So that is 11N over 12 times 10 over 12 times 9 over 12. Now, if he takes 4 over 12, he does not take 8 over 12, and that is, of course, what will calculate how much is remaining. And I hope by now you can see this pattern. And just to beat this home, we'll do one more. And K is 5. That means that pirate will take 5 over 12. If he takes 5 over 12, he does not take 7 over 12. And therefore 7 over 12 is the fraction of this amount that he leaves remaining. And that's 11N over 12 times 10 over 12 times 9 over 12 and times 8 over 12. You will get to eventually the 11th pirate, and after the 11th pirate is done, what will be remaining is 11 over N over 12 times 10 over 12, 9 over 12, and so on, right? 8 over 12. 7, 6, 5, 4, 3, 2, 1. And these are all over 12. So this is what is remaining after the 11th pirate. And since this is what's remaining, this is what the 12th pirate gets, because the 12th pirate gets 12 over 12, which is 1 of this. So this doesn't need to be, broken down anymore. He's basically going to get 12 over 12. So if you really want to put it in, you can say he gets 12 over 12 of this, and that would be the amount that the 12th pirate gets. So this is what we have to figure out. Now, they don't obviously give us the n, so we have to figure out what does this possibly be for it to be an integer, because the value that he gets is a whole number. Okay, so we got to do some fancy math here. Not too fancy. We've got n, and then we've got all these different fractions, right? So let's, first thing is break them down into lowest terms. 5 over 6, 3 over 4, 2 over 3, 7 over 12. I'm just breaking these down into lowest terms. Hopefully that will help us. 1 over 3, 1 over 4, 1 over 6, and then 1 over 12. Okay. In order for this to be an integer, that means that n has to cancel with the denominator. And once it does, the numerator is the amount of gold coins that 12th pirate receives. Correct? But I think I can probably break this down a little bit further. For example, the 3 times 2 is a 6, but that cancels with that. And I think that's it, because all the remaining ones, 11, 5, 7, and 5, those are prime numbers. So that's not going to be broken down. So in order for this to be some integer, and we want n to be as small as possible, we want basically this remaining denominator to cancel out with n, since that is in the numerator. If it cancels out, the only thing that will be remaining are these numbers right here. The 11, the 5, the 7, and the 5, because all the other ones are 1s. So if n is equal to that denominator, the only thing that's left is 11 times 5 times 7 times 5, and that will be our integer, and that represents how many gold coins the 12th pirate receives. And remember, we want n to be as small as possible, so the smallest it can be is to match identical to that denominator. And there we go. This is going to be my answer. Therefore, 11 times 5 times 7 times 5 is 1925. And that's how many coins that 12th pirate will get. So 1925, and therefore that is D for number 21. 6 spheres of radius 1 are positioned so that their centers are at the vertices of a regular hexagon of side length 2. The 6 spheres are internally tangent to a larger sphere whose center is the center of the hexagon. An 8th sphere is externally tangent to the 6 smaller spheres and internally tangent to the larger sphere. What is the radius of the 8th sphere? Most difficult part about this question is just sort of figuring out the 3D nature of it. So the first part of the question tells you that you have these 6 spheres, right? A, B, C, D, E, F, G. A, B, C, D, E, F, actually. And then the centers of them, if you join them up, they would make this hexagon. And there's a larger sphere that is represented by that large circle, and its center is the center of that hexagon. So that first diagram, I think, is pretty straightforward. Now we have to start thinking about this first diagram a little bit more before we head on to the next part, which is that 8th sphere. So let's not talk about the 8th sphere just yet. First, let's understand this first diagram. These tiny little spheres, they're spheres, remember, 3D, they told me that they have a radius of 1. So that's why this is labeled 1. And then, when you consider the fact that they're tangent to each other, from here to here is 1, from here to here is 1, and therefore that's why each side of that hexagon has a side length of 2. So that's pretty straightforward. But then when you draw lines from the vertices of the hexagon to the center right there, that's going to create a triangle like that. Now that triangle is equilateral. Now how do you know that? Well, this is a hexagon, and the internal angles of a hexagon are equal to 120. So this is 120. If you cut that in half by drawing a line down, this becomes 60. And in a very similar way, if you did the same thing here, that would become 60. So 60, 60, and therefore this must be 60. So therefore, those are equilateral triangles. And since they're equilateral, all three sides are the same. So if that was 2, then this is 2. Correct? So that's how you know that from here to here is 2. Well, from here all the way to here is the radius of that larger sphere. So the radius of the large sphere is 3, since from here to here is 2, and from here to here is 1. All right, so I think that's about as much as we need to know about that first diagram. Now the second diagram, what we have to do is envision this, a bird's eye view of this diagram. So this is A, and this is A. So that's what we're comparing. And then this sphere is D, and in this diagram, we've placed it here. Okay, so we're drawing a line from the center of A to the center of D. Well, on this diagram, we can do that right here. And from here to here would be 2, and from here to here would be 2. So if we do the same thing on that diagram over there on the right, from here to here would be 2. So I'll just label that 2 right there. And now, this big circle all the way around is the sphere that is represented by that circle. The only thing is that the orientation is different. Here, I was looking at it sort of like a bird's eye view, but here I'm looking at it from a slightly different angle. I'm looking at it from sort of the side, I guess. And like this would be the bird's eye view, but now I'm looking at it from the side. The 8th sphere is represented right here. This is the 8th sphere. It's placed in a way so that it's tangent to all those little guys. So as you can see, it's tangent to A and D. But it's also tangent to the big one, right? Up here. There's a tangent point right there. So we've squeezed it in right there. And now we have to figure out the radius of this 8th sphere. So I'll call it small r. So that's small r. And then from here to here is also small r. And then the distance from here to here, well, that's just 1 because that's the radius of the small sphere. The distance from here to here, well, first of all, what is the distance from there to there? That's the radius, this guy, the radius of that big one all the way around. So that's 3. So if from here to here is 3, and from here to here is r, this distance right here will be 3 minus r. And then therefore we've got a nice Pythagorean relationship, and we can pretty easily figure this out. So it's going to be 2 squared plus 3 minus r squared is equal to 1 plus r squared. If you expand this out, you're going to get 4 plus 9 minus 6r plus r squared is equal to 1 plus 2r plus r squared. The r squareds cancel on both sides. This gives me 13 minus 6r is equal to 1 plus 2r. If I bring the 1 over, it becomes 12. Bring the 6r over, that becomes 8r. And therefore r is 12 over 8. In lowest terms, r will be 3 over 2. And therefore, for number 22, the answer is B. I think the most challenging part about this was trying to visualize this scenario as to how exactly all of these spheres fit together so that they're tangent to one another. in triangle ABC, AB is 86 and AC is 97. A circle with center A and radius AB intersects BC at points B and X. Moreover, BX and CX have integer lengths. What is BC? A little bit of a primer before I begin the question. I have to show you something called a power of point theorem for a circle. And some of you may know this, but if you don't, not to worry, I'll show you. So if you have a circle like this, or any such circle, and you draw, let's say, some sort of a line like that, and then you connect that line to another point, and let's label this now. Let's say this is A, this point is B, where that line cuts through that circle. This is C, this is D, and this is E. Power of point theorem states that CB, this distance right here, multiplied by CA, which would be this full distance from C to A, is equivalent to CD, which is the distance from there to there, multiplied by the full distance from C to E, like that. So it's a fairly straightforward theorem, and we're going to use that in our question. So in our question, we are given another scenario. We have, let's say, pretty big circle. And we are told that we've got some sort of a center here, denoted by A. And we have to extend it to some B. And then that B, therefore, is extended to cut through that circle at some point X. And eventually it gets to C. So that's the setup of the question. Now let's label what they give us. AB is 86. So 86 basically represents the radius, since A is the center. And they even tell me that the radius is AB. Well, the way I drew it, I can extend it here, and therefore this is 86, the distance from there to there. And I can extend it to here, and that is also 86. So that point right there on the circle, I'll just call Y. And AC, they told me it was 97. So from here to here is 97, but from here to here is 86. So that means this distance right there, that little guy, is 11, right? It's basically 97 minus 86. Okay, so now that we've done our labeling, now we can use the power of point theorem here. So in a very similar way, exactly like that, it would be CX times CB, or BC, whichever way you want to write it. You can write BC if you like, since they're asking for BC. And then that is equivalent to CY times CZ. All right, no tricks, just applying the power of point theorem exactly the way it is. Let's fill in what we know. CX we don't know. BC we can break up into CX plus BX. And then CY we do know, that's 11. And then CZ is all the way from C to Z. So that's basically going to be 11 plus 86 plus 86, which is 183. Like that. And then 11's already prime. 183 is 3 times 61. That's the prime factors of 183. And this is still CX plus BX. Now at this point we have to do a little bit of thinking here. Basically we have two numbers that multiply together to give us this. Now how do we do that? Also considering CX is here, but CX is also here. Well, if you fiddle around with this, you'll see that the only way to do this is to make this guy 33, and that way this would be 33 and 28, or this would basically be 61. So This 61 is here, and this 3 times 11 is here. That's the only way to make that work. And I think that's all they really are asking for. See, the CX plus BX is CB. Or BC, right? So that's it. This is BC. And it's equal to 61. So if you use the power of point theorem, you can see that you can get the answer pretty quickly. So number 23, the answer is 61, which would be D. Central High School is competing against Northern High School in a backgammon match. Each school has 3 players, and the contest rules require that each player play 2 games against each of the other school's players. The match takes place in 6 rounds, with 3 games played simultaneously in each round. How many different ways can the match be scheduled? Well, I will let the Central High School players be called C's and the Northern High School players be called N's. So, if I make a little table, I've got C1 for the first player from Central and N1 for the first player from Northern. And then similarly, because they each have to play each other twice, I've got to make a little list here like this. So N2, N2, N3, N3, like that. And in a very similar way, I've got to do the exact same thing for C2, like this. So N1, N1, N2, N2, N3, N3, like that. And in the very similar way, the same thing for C3. And to make things easier to understand, we'll just call these combinations A, this combination B, this combination C. This combination will be D, E for that, F, and then we'll call this G, H, and I. All right, so here we go. And remember, we have 6 rounds. So I've got actually, interestingly, 2 methods. There's method 1 and then there's method 2. And method 2 actually has 2 iterations or 2 ways, A and B. So we'll go through all and then of course we'll add them all up. So first method basically means that you have to, in each of these rounds, right, there's round 1 all the way to round 6, we have to choose. So what are the combinations? You can have A, E, I, right? You can have either this, this, and this. That's one way of filling around, A, E, I. Another way of filling around is A, F, H. That would be C1, N1, C2, N3, and C3, N2. That's another way of filling around. Another way is B, D, I. That's C1, N1, C1, N2, C2, N1, and C3, N3. That's another way of making a round. Another way is BFG. And the last 2 ways of making a round are CDH and CEG. Now, I can only choose one of these for this round. So what I'll do is I'll just choose this guy. So this will be what I choose for my round. Okay? And in a very similar way, all of these can be placed as choices. But since I've already chosen this guy, now for the next round, I can really only choose one of the remaining 5 of these 5. So for the first round, I had 6 possible choices. So I'll put 6 up here. But for the next round, I've only got these 5. So I'll choose one of these 5. Let's say I choose this guy. And then for the next round, I've only got these ones left. B, F, G, C, D, H, and C, E, G. So I've only got 4 choices. So I'll choose one of these. Let's say I choose this one. I might as well go in order. Why not? For the 4th round, I've only got BFG, CDH, and CEG left. So I only have 3 possible choices. And let's say I choose BFG. For the 5th round, I only have CDH and CEG left. And let's say I choose CDH. And then for the last round, by default, I only have 1, and that is CEG. So in order to get the total number, of course, I have to multiply them all. So it's 6 times 5 times 4 times 3 times 2 times 1. And that is equivalent to 720. So method number 1 gives me 720 ways of making arrangements, possible combinations. Now we get to method 2, and method 2 is as follows. What you do is you first select something. So let's say I selected an AEI, very similar to the first one. But in the second round, again, I choose AEI, like that. And then since my A's are gone, I can't really choose AFH because I've already had A play twice. So the only selection I'm doing for the the third round is now moving on to my B's because A is done. So I say, okay, I'll choose B, F, G, let's say. And then I do BFG again. So I use the exact same for 2 rounds in a row. Now that the B's are done, I move to the C and I choose, say, CDH. And I use the same twice. So that's method number 2. And when you do it that way, it's very similar. It's also 720 because it's also 6 times 5. But because you have 2 that are the same 3 times, you have to divide this by 2 times 2 times 2, because otherwise you have a whole bunch of scenarios that are identical. That's why you have to divide by 8. And when you do, you get 90. The other scenario is identical in the same way, but the only difference is that you're using different combinations. So AFH, AFH twice, and then BDI, BDI twice, and then you're using CEG and CEG. And identical to what's above, the number of combinations would again be 720, but then because you have 2 that are the same, 2 that are the same, and 2 that are the same, you have to divide by 2 times 2 times 2 to get unique combinations. And when you do, you get 90. So the total answer to this question is this 720 plus this 90 plus this 90. And when you add that up, you get 900. And therefore, number 24, the answer is E. All 20 diagonals are drawn in a regular octagon. At how many distinct points in the interior of the octagon, not on the boundary, do 2 or more diagonals intersect? Here is the non-scientific way. You just draw it. Draw your octagon, represented by this yellow boundary, 1, 2, 3, 4, 5, 6, 7, 8 sides, and then you just take your ruler, and I think rulers are allowed, I'm not really sure, but they should be, and just start drawing all the 20 diagonals. Shouldn't take that long to draw 20 lines, and then start counting all the intersection points. And the intersection points in this diagram represented by the red dots. And when you count all the red dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. And therefore, in a non-scientific way, we got the answer, which is A for number 25.